This is lecture 5 of our class, Symmetry, Structure, and Tensor Properties and Materials. And in this lecture, we're going to just prepare a little bit more for general combination of operations. So we're going to have just a little summary just to make sure that we understand all of our operations, and then we're going to talk about the symbols that we use. We've already introduced that, but I just want to summarize that. Just to refresh your memory, the operations in 2D, right, that we have, and we did our first combination theorem, which was taking a translation vector and combining it with a rotation operation. And that was in the last lecture. We're going to continue with that, but I just want to make sure that we summarize all the symbols, because as you saw last time, in combining that, we want to put like the rotation axis there, and we have to have a symbol affiliated with it. So let's just recall that, of course, we had a translation, and we had a rotation, and we had mirror plane. So we just want to be formal about what the operation is in the diagrams that we do. How do we represent that particular operation? What about when we want to operate, what is the operator symbol itself, and that sort of thing. Now we mentioned before that this is in 2D, and in 3D, we're not going to do 3D right now, but just to remind you that in 3D inversion is possible, and in inversion you have the ability to do, in inversion you have the ability to actually invert all three coordinates. So here x, y, z go to x bar, y bar, z bar, where the bar just means the negative version, right? Now the way you can see that this is not possible in 2D is because we've already done this operation in 2D, and that, as we know, is the twofold axis, where we have zoop, a 180-degree flip, and if I did that correctly, oops, I did it wrong that way, sorry. 180-degree rotation about the center, a pi, and already you start to see some of the symbols I want to make very clear in the next view graph. But so obviously you can't have inversion in 2D, because if I do the same, just take the negative of each coordinate, I end up with a twofold axis, which you've already talked about. So there is no inversion operation in 2D. So we showed you before in the complete derivation that if we combine a rotation operation here, this would have to be some integer of the translation vector for everything to work out, right? We ended up showing that the fivefold axis can't fill space. There's just basically no way to end up. If I do integral numbers of p, I don't end up with a fivefold, and that's how we determined that there was no pentagon possible. Within the angles that are possible, there's a simplistic solution, of course, which is 2 pi, where n equals 1, but that's a trivial solution because 2 pi is 360, so there's nothing going on there. We had pointed out that we have 180-degree so we can have 120 degrees, we can have 90 degrees, and we can have a 60-degree as well. What that means is that you can think about just writing those in the following way, and that, of course, this has to be true as well, that if I start off with a subset. Remember, what this determined was a subset, that there can't be a pentagon. But then within that subset, basically this has to be true. Anytime I rotate, obviously, through alpha, I better have another translation data point, right? That's what this says as well. And so, you can think of it, oh yeah, well, if this is alpha, then after n alphas, I better end up at this same point, right? So as a subset, remember, because you can divide 360 by all sorts of numbers. So this is the first derivation that has to happen, right? But then after we determine that we're going to have these angles, you can write them this way, just as an index. And that's important because we're going to use n in our table. That's why we have to introduce this. So once we introduce the angles, the rotations that can fill space and are consistent with the lattice, then we can write n alpha equals 2 pi for those angles. And by definition, of course, we know that all of these will satisfy this equation because they satisfy this one, which means that after n number of rotations, of course, you're going to end up at the same translation point. Okay, so it's just notation. We could have said, we're going to continue to talk about the rotations as a subscript, right? But we're going to use n as to identify. Really, if you think about it, when we say a two-fold axis, we say a three-fold axis. So really what this is saying is it's a n-fold axis, right? So that's just the terminology for the table. So let's fill out that table. So, if I look at this, we can now summarize all of our operations, but also assign these symbols that we'll use going forward. So we already talked about how our translation operation we show, remember, from point to point as a single operation. We've already talked about the set. So we use this traditional symbol for a set of elements, and we already showed that there's just some integer number of t, which is all of the possible lattice points, right? It's 1 and 2t, 3t, 4t, 5t, etc. And the generic symbol we've already been using when we show where t is operating on. And so the symbol is the same, except we always show it going from some point to point like that. But there's just no unique starting point in space because t operates on another lattice point. And where we put that lattice point on this piece of paper is up to me, right? But once we have one, then that's where it goes. So now let's think about our mirror plane. We're going to represent the operator. So we say single operation, we really mean the operator in a way, right? So the operator, we write that mathematically. The operation is going to be sigma, but the set of operations will use the symbol m to represent all of the mirror planes. And then the way we're going to show that in using a symbol, we're going to draw this line, and typically we might put an m at the bottom, but that's not necessary. It's just this plane in general. And for example, if we have an object here, it'll be reflected across over there, right? And then we have a rotation, which we've talked about, and there the A is the point about which we operate, right? And then there'll be a set of these that are maybe in something where remember n equals 2 pi over alpha, which is really just the n is the like two-fold or three-fold or four-fold axis, right? N is the fold part, the number. And then the symbols we already talked about: a two-fold axis, a three-fold axis, a 4-fold axis and a 6-fold axis. Right? Finally, something we haven't talked about, but in group theory will be important, there's a symbol to be complete and three-dimensional. We have the inversion operation, and that's represented in group theory as 1 bar. Makes sense, right? Because the number 1 negative is, of course, itself, but that's kind of to show it's an inversion operation, which means that, of course, you just, as we showed already, just x, y, z becomes negative x, negative y, negative z. The set of operations represented by the same thing, and in 3D, when we get there, an inversion point is represented by kind of a little circle, not to be confused with any other symbol. A little open circle. If you can't tell, that's an open circle. I'll draw another one here. So a small little open circle about that center point at which you're being inverted. So that's going to be our table of operations. Of course, we're going to use the top 3 in 2D right now. And that's what we'll start with the next lecture.